We talked about equilibrium constants and their expressions, the equations that sort of define them for a particular reaction last week. And so we talked about them in terms of concentration in molarity. But for a gas reaction, it can be more convenient to express that concentration in terms of its partial pressure. And what we're going to see is that the partial pressure of a gas in a mixture is directly proportional to its concentration. So if we want to express the equilibrium constant in terms of pressure, it takes the same form, but we're using partial pressures instead of molarities. So for this one, we've got SO2 squared times O divided by SO3 squared. In terms of concentration, it's all the same things, same exponents, but it's partial pressures. So the value of Kc and Kp are sometimes the same, but not always. But there's definitely a relationship to them, between them. So the partial pressure of a gas in atmospheres is proportional to the concentration and molarity, but it is not the same. So let's look at that relationship. And this starts with the ideal gas law. So PV equals nRT. Well, molarity is moles per liter, right? Are moles and liters in here anywhere? Yeah, we have N for moles and V for volume in liters, right? So let's rearrange this to put those guys on the same side of the equation. So here I've got my N over there. It's in the numerator where I want it, so I'm not going to mess with that. I'm going to divide by V on both sides. The V's cancel out. And I'm going to divide by RT on both sides. So the R's and the T's over here cancel out. And now I have N divided by V is equal to P divided by RT. And that is equal to the molarity of a gas. In Chem 1A, we always talked about pressures of gases. We did not talk about the molarity of a gas. But molarity is moles per liter, and you can describe how many moles per liter of this gas are there. Any questions? So I'm going to derive the relationship between Kp and Kc. I want you to follow along, see if I make any mistakes. I'm not going to expect you to regurgitate this on an exam, but I think it's good to see how the math works out, and you should not always just believe what people tell you, right? It's like, well, yeah, you said it's that, why? Okay, I'm going to show you why. So we're going to use the molarity of A is equal to P, the partial pressure of A over RT. And we just saw where that came from. This molarity of the gas is N over V, right? Here we've got a generic equation, and so we'll start by writing the expression for equilibrium constant in terms of concentration, right? So that's going to be the products. So pick a pen. Products are C and D divided by the reactants, A and B. And the coefficient becomes the exponent in this equation, right? So this is C, and this is lower d, and this is little a and little b. Okay? So now what we're going to do is, instead of having the concentration of A, the molarity of A, we're going to put in something that it equals, right? So PA over RT is equal to that, and so I'm going to substitute this in here. And C is equal to the partial pressure of C over RT, and so I'm going to sub in for all these other guys. It's going to get messy. So here we have the partial pressure of C over RT to the C power, partial pressure of D over RT to the D power, partial pressure of A over RT to the A power, and the partial pressure of B over RT to the B power. Any questions about what happened there? So this is also a description of KC. Well, that's a mess, right? Let's think about this chemical reaction occurring. Is R changing the gas constant? No, definitely not. We can control whether the temperature changes or not. So we can hold the temperature constant, and then this also is a constant. And that's how we get the molarity being directly proportional to the partial pressure. Part of the proportionality constant is the gas constant, but also the temperature of the gas. So you change the temperature, the gas is going to expand or contract, and that's going to change its concentration, right? But if we keep the same temperature, it'll be the same. So we have divided by RT in all of these, and so we're going to factor those out. So I've got PC to the C, PD to the D, divided by PA to the A, and PB to the B. Okay, so I pulled those out. We can't just abandon the rest of it. So this is 1 over RT to the C times 1 over RT to the D, 1 over RT to the A, 1 over RT to the B. Sometimes things get worse before they get better, right? Cleaning out a closet, you have to make more of a mess before you can reduce the original mess. Okay, so now we have this 1 over RT, and it's multiplied and divided here, and all that's different about these is the exponents. So we can combine these terms as well. Let's see the best way to do this. The best way to do this is to cheat a little bit and copy things. So we have 1 over RT up there, and we have 1 over RT down here. Let's just think about exponents for a minute. If I have x to the A times x to the B, we add the exponents, right? So that's the same as x to the A plus B. Okay. Little math review there. So here I've got 1 over RT to the C times 1 over RT to the D. And so that's 1 over RT to the C plus D. And then in the denominator, we have A plus B. So it's getting a little smaller, still pretty messy. Well, if I have x to the A divided by x to the B, that is equal to x to the a minus b. It's great if you have a good grasp of exponents. If you don't, you can still be successful, okay? So when we divide things raised to a power, then we subtract the exponents. So here I have this guy raised to that power divided by this guy raised to this power. So that is the same as 1 over RT to the C plus D minus A plus B. Okay? I guess I could have simplified this a long time ago. What does this equal? KP, right? So KP is the same form, but with partial pressures instead of concentrations. So I should have done this before, but I didn't think of it. That is KP. What we're looking for here is KP equals what? What's the best way to explain this? There's different ways to think about it. So to solve this for KP, I need to divide both sides by this, right? It's kind of big, right? A big mess. So those messes cancel out, right? So here I have a fraction in the denominator. I have 1 over RT. So let's think about that in terms of x. If I have 1 over x, that is 1 over x to the negative 1. This does equal x to the negative 1. But if I have 1 over x, that just ends up being x, right? This is 1 over x to the minus 1. And 1 over is change the sign, and so we get back to x. So over here, then, if I want to bring this up and simplify it, 1 over RT is RT in the numerator, right? So I'm going to end up with KP is equal to KC times RT to the C plus D minus A plus B. So we're going to define delta N as being C plus D minus A plus B. So then we end up with the relationship KP is equal to KC times RT raised to the power of delta N. what delta N is we're looking at the moles of gas products added together, and we're subtracting the moles of gas reactants added together. If delta N is 0, what happens to that RT term? It becomes 1, and Kp equals Kc. So that's our end result. And that equation is on your useful information for Chem 1B exams handout that you get for exams. So you do not have to memorize that equation. You need to just remember how to use it. I remember in physics in college, they gave us a page with all these equations. And we were like, oh, this is awesome. We don't have to memorize anything. And then we quickly realized, but those are useless if you don't know what to do with them, right? But their point was, if you use those equations all the time, you remember them. If you don't use them all the time, as a career physicist, what do? You look them up, right, when you need them. So here is your reference sheet. We can look them up on here, but you need to learn how to use them. So that's what I'm doing with you guys. So delta N represents the difference between the number of moles of gas products and gas reactants. So in our generic equation here, we are assuming that all of these are gases, because it's only the gases that are going to have that RT in them. So if we have total number of moles of gas the same before and after, there's no change in the moles of gas, then if we look back here, what's going to happen is all of those RTs would just cancel out, and Kc will equal Kp. And that's what that derivation is telling us. Okay. Consider the following reaction and corresponding value of Kc. What is the value of Kp at this temperature? Well, the equation we would use for this is Kp is equal to Kc times RT to the delta N. So, first thing we should do is find out what is delta N for this reaction. It's the total number of moles of gas products. Remember, delta is almost always final minus initial. So it's final moles of gas minus initial moles of gas. So final moles of gas is 2, and then how many initial moles of gas do we have? 2. We have 1 plus 1. So that adds up to 0. We're always happy when this happens because it makes things easier. So then Kp is equal to Kc, and all we have to do is write down the number we were given. Because when we put that in here, Kc times RT to the 0 is just Kc. If you forget that something to the 0 power is 1, you could plug this in on your calculator, and your calculator will do it for you. There's nothing wrong with that. It's just a little extra work because you have to actually type in some numbers here. Temperatures given, remember that has to be in Kelvin anytime we're dealing with gases. And then this constant here, which one are we going to use? We have 2 values. We've been using the 8.314 joules per mole Kelvin, but there's also 0.08206 liters atmospheres per mole Kelvin. This is one we used with gas laws. How do we know which one to use? Pardon me? Yeah, we're going to look at the units, right? So here, we've got pressures of gases, right? And so we want to use this one with pressures of gases. If we're doing something that has energy in it, we want to use this one. There is a relationship between liter atmospheres and joules. But instead of converting these back and forth, we just have these two available to us. Any questions? Okay, units. So officially, formally, the values of concentration or the partial pressures used in those expressions are not the actual concentration or partial pressure. It's a ratio of the partial pressure or concentration to a reference value. Well, the reference value is going to be exactly 1 molar or exactly 1 atmosphere. So what ends up happening is that the equilibrium constant has no units because of this. So in the expression, when we want to use 3.7 molar, what we're really putting in there, what we're really using is 3.7 molar over 1 molar. This is a reference value. And so then the units cancel out for all of the terms in that expression. And you could view this in a couple of different ways. One is that it's just a genius way of getting around the fact that otherwise equilibrium constants would have all kinds of crazy units. We might have molarity cubed or molarity the negative 1/2 or something, and they'd all be different. And by defining them this way, we don't have to keep track of any of those units. So, as long as we express concentration and molarity and the partial pressure in atmospheres, we can drop the units in equilibrium constant expressions. Any questions? Okay. Under which circumstances are Kp and Kc equal for the reaction shown here? If A plus B equals C plus D, if the reaction is reversible, or if the equilibrium constant is small. It's going to be A, right? Because Kp is equal to Kc when delta N is 0, delta N is C plus D minus A plus B. Any questions?